At 3:17 p.m., my phone started vibrating nonstop. PagerDuty triggered a high-priority alert for elevated 5xx errors on the public API. At almost the same time, our Slack incident channel auto created itself, and the bot posted a link to the Grafana dashboard. Error rate had jumped from under 1% to nearly 40% in less than 2 minutes. What made it strange was the load balancer metrics. The cloud dashboard showed healthy targets, no instances marked unhealthy, no surge in rejected connections. Latency at the edge looked normal. Everything on the infrastructure side looked perfect. But customers were posting screenshots in our support channel. Login spinning. Checkout failing. Some users getting blank pages. The load balancer was green across the board. The app, however, was clearly not. We were flying blind. Environment context. We were running on AWS across 2 availability zones in a single region. The setup was robust and redundant. The application was deployed on EKS with around 40 worker nodes split across on-demand and spot instances. Traffic averaged about 25,000 requests per minute during peak hours. That afternoon, we were slightly above normal due to a marketing campaign. The core application consisted of a stateless API layer written in Go, deployed as a Kubernetes deployment with 20 replicas. Behind that was an RDS PostgreSQL primary with 1 read replica. We also had Redis for session caching and rate limiting. The service was exposed through an AWS application load balancer managed by the Kubernetes ingress controller. Health checks were configured to hit the readiness endpoint on each pod. On paper, every node was passing with flying colors. CI and CD were handled by GitHub Actions building Docker images, pushing to ECR, and Argo CD syncing changes into the cluster. Monitoring was a mix of Prometheus, Grafana, and CloudWatch. Logs were shipped via Fluent Bit into Elasticsearch. On paper, it was a fairly standard resilient setup. We had no reason to expect a total system failure. Initial symptoms. From the user perspective, logins were failing intermittently. Authenticated actions returned nothing but 500s. Grafana showed a sharp spike in HTTP 500 responses coming specifically from the login and session validation endpoints. CPU usage on the pods was slightly elevated but not saturated. Memory was stable. No kills. No restarts. Pods were healthy. The load balancer showed healthy target groups. No abnormal 502 or 504 errors at the edge. Network throughput was consistent. Database metrics were within expected ranges. CPU on RDS was at about 60%. Connection count was slightly higher but safe. What looked suspicious was application-level latency. P95 latency for the login endpoint had jumped from 120 milliseconds to over 2 seconds. My first hypothesis was uneven routing or shallow health checks. Maybe the readiness probe was passing while the app was degraded. I checked the ingress logs. I exec'd into a pod and curled the readiness endpoint. It returned 200 immediately. The pod thought it was fine. Next was database saturation. RDS slow query logs showed a slight increase in duration for one specific query, session validation. Meanwhile, support escalated the incident to the product lead. Slack started filling with questions about revenue impact. Marketing paused the campaign. Leadership wanted an ETA. We debated scaling the API, but feared amplifying the problem if the database was the bottleneck. I increased replicas from 20 to 30 anyway. HPA had not triggered because CPU thresholds were not breached. Error rates dipped, but latency stayed high. Then I checked Redis. Command latency had spiked. I ran Redis CLI and saw increased response times for every single GET operation. Session validation depended on Redis lookups. If Redis slowed down, login would fail, but traffic wasn't high enough to kill Redis. Why now? Looking at history, I saw a new API version had been deployed 40 minutes before the incident. It was a minor change for session metadata. The diff showed we were performing an additional lookup and extending session expiration on every single request. More writes to Redis. Write commands per second had nearly doubled. Combined with the marketing spike, we were pushing far more operations than ever before. Escalation widened. Our database engineer and backend lead joined. We discussed whether to roll back or apply a forward fix under pressure. The root cause. The new session logic used a Lua script for atomic updates. It was more expensive than simple get and set operations. Under load, those scripts were blocking other commands because Redis is single-threaded. Latency accumulated and API requests timed out. The load balancer reported healthy targets because readiness probes didn't exercise the session path. They only checked a lightweight endpoint. We had 2 options, rollback or toggle a feature flag. Given the pressure, we chose the safety of a rollback. Argo CD made it easy. We reverted the image tag and synced. Within 5 minutes, new pods with the old version were running and the errors began to fade. I watched Redis command latency drop almost immediately. Write operations normalized. API latency gradually returned to baseline. Error rates fell from 40% back under 1%. We monitored for 30 minutes before finally declaring the incident mitigated. Total customer impact, 45 minutes of intermittent failures. A small window, but a massive lesson for our engineering culture. Post-mortem reflection. What failed was our assumption that a small logic change would have a negligible performance impact. Detection was weak because our readiness probe did not reflect real user paths. We checked the process, not its critical dependencies. We didn't have alerting tied directly to Redis command latency. We only saw it after digging manually. That has to change. Our wrong assumption was that infrastructure health equates to user experience. All cloud dashboards were green, but application semantics were degraded. Architecturally, we relied heavily on a single Redis instance without rate limiting or circuit breaking in the API layer. Organizationally, the change passed review but hadn't been load tested against realistic traffic patterns. Performance is a feature. Engineering lessons. Health checks must represent critical user flows. If login is core, readiness must exercise its dependency path. Single-threaded dependencies like Redis can become silent bottlenecks when command complexity increases. We can't ignore them. Treat performance changes as functional changes. Adding a Lua script in a hot path is never a minor refactor. Review it like a feature. Observability must include dependency-level metrics, command latency and queue depth, not just high-level CPU and memory. Finally, rollback speed is a reliability feature. Because our pipeline was clean and versioned, we could revert safely and quickly. That day reminded me, when dashboards say everything is healthy but users disagree, the truth is hidden in the gaps between components. Always monitor the user experience, not just the infrastructure. This was the silent Redis bottleneck. Thank you for watching.